So this video will cover carbon-hydrogen combustion analyzers. It's basically a type of analysis that takes a hydrocarbon, an unknown hydrocarbon, subjects it to complete combustion, so burn it, and the number they gave you will be the mass of the carbon dioxide and water that's produced, and from there you are told to find the formulas. So either the empirical or the molecular formula. So if we take a look at this one question from your textbook, it says a 2.524 gram sample of a compound contains carbon, hydrogen, and oxygen. So this is one where you have oxygen also, as well as carbon and hydrogen. Tends to be a little more complicated because there's this one extra step that's required. The sample is subjected to carbon-hydrogen analysis. 3.703 grams of carbon dioxide and 1.514 grams of water are collected. A. Determine the empirical formula of a compound. B. If one molecule of the compound contains 12 atoms of hydrogen, what is the molecular formula of the compound? So usually in a question like this where they ask us for the molecular formula of the compound, they would give us the molar mass of the compound. And then in class, I think I showed you 3 ways of doing this. The 2 easiest and fastest ways both require you to have the molar mass of the compound, but you don't. They didn't give it to you. So what that means is that we are limited to the longest way of doing this type of questions. Okay, but regardless, we can start by writing the equation for combustion. So you're taking a compound that has carbon, hydrogen, and oxygen, and you're burning it, so that requires you to burn oxygen, and it always makes carbon dioxide and water. So spread your equation out so they can do math under each compound. You can start off by writing all the numbers down. So you have 2.52 grams, 524 grams of the compound initially, which after you burn it, produces 3.703 grams of carbon dioxide and 514 grams of water. So we start planning. I'm going to go to the next page and start planning this. When I'm asking you for a molecular formula or empirical formula, really means that they're asking for these numbers here. And then these numbers are, again, mole ratio. So you need mole ratio of C to H to O. But in order to get that, you need the mass of C and the mass of H and the mass of O. But you don't have that. The only numbers they gave you is the mass of CO2 and the mass of H2O. So somehow we have to get from the mass of we have to get from the mass of carbon dioxide to the mass of carbon, and then we have to find the mass of hydrogen inside mass of water, and then mass of oxygen from somewhere else. Okay, so remember percent composition, right? So percent composition, again, why are we using percent composition? The reason is because percent composition is really the mass of an element from the mass of the compound. So when we have percent composition, it allows us to find the mass of carbon from carbon dioxide, which is exactly what we want. We want to know what the mass of carbon is from carbon dioxide, from a certain amount of carbon dioxide. And we also want to know what how much mass, what is the mass of hydrogen from the mass of water. And we don't have any amount of water or carbon dioxide. We have so we want to know what is the mass of hydrogen from, or how much hydrogen's mass would be from 1.514 grams of water. So how much of this mass actually comes from hydrogen, and how much of this mass actually comes from carbon dioxide, which is what this means, right? How much of the total mass comes from carbon, and how much of this total mass comes from hydrogen. And that's why we're going to use percent composition in this step. Okay, so let's try that. So we're going to take 3.703 grams, and we're going to say that I'm going to write in a number first. So why did I do this? Why did I do this here? Okay, what is the 12 over 44? Because we have carbon dioxide, right? We can say that in 1 mole of carbon dioxide, 12 grams comes from carbon, and then the molar mass of carbon dioxide is 44 grams. So if you convert that to a percentage, that is 0.277%, sorry, 0.277, which is 27.7%. But instead of doing all this work here, why don't we just leave it as a fraction? So why don't we just cross this out and say, why don't we just use this fraction directly, which gives us the same number, and put it in here. So what we're doing here, we're saying that this, which is 27.7% of the total mass, right? We're multiplying, remember? We're saying that 12 over 44, which is 27.7% of the total mass, comes from carbon. So in here, what we calculated is that inside 3.703 grams of carbon dioxide, 1.0099 grams inside here comes from carbon. So this is the mass of carbon inside this amount of carbon dioxide. So this is just a short way of using percent composition without having to write it fully. Okay, because it's the same number. These two things are the same number anyway. So we'll just keep this instead of writing out the full thing. So let's do the same thing for water. So here we can say that inside 1.514 grams of water, we have 0.1862. 1682 grams of hydrogen. Again, why this? It's because if you look at the percent composition of hydrogen, you have 2 hydrogen for the entire molar mass of water, which if you want to calculate it, that is 0.11111 or 11.1%. So again, instead of writing this all out, it's going to be 2 over 18 anyways. This is equal to 11%. So why don't we just keep this instead of writing this all out? But ultimately, what we care about are these two numbers. Now that we have those two numbers, we can actually go ahead and subtract and get the mass of oxygen, because we know that this mass here is mass of carbon plus all the hydrogen plus all the oxygen. So if we were to subtract mass of carbon and subtract mass of hydrogen, then that would give us the mass of oxygen. So we take 2.524 minus 1.0099, that's carbon that we just calculated from here, minus 0.1682, that's the mass of hydrogen that we just calculated from here. So after that, we have 1.3459 grams of mass remaining, and that's oxygen. So we have mass of oxygen, mass of carbon, mass of hydrogen. So we're going to take those numbers. So we have mass of carbon. We can divide it by the molar mass to get moles of carbon. We have mass of hydrogen. We can divide that by the mass of hydrogen to get moles of hydrogen. We have mass of oxygen. We can divide that by the molar mass of oxygen atoms to get moles of oxygen. So if we do that, (0.08412), it's how many moles of oxygen we have. (0.1669) is the moles of hydrogen that we have. And 0.08416 is the moles of carbon that we have. So again, if you're getting lost, go back to our plan. What did we just do? We just found out the mass of carbon and the mass of hydrogen from inside these amount of carbon dioxide water. And then from subtraction, we got the mass of oxygen. We converted to moles. Now we are ready to set a mole ratio that will give us these numbers. So we're almost there. So in a mole ratio, I'm just going to go very quickly. This is already our ratio to 0.1669 to 0.08412. That's carbon to hydrogen to oxygen. Again, the trick is to divide by the lowest number, which is 0.08412. So that would give us 1 to 1, and then to 2, or very close to 2. 1.98, so close enough to 2. So now that we have these nice whole numbers, our formula is C1, we don't write the 1, H2O1. But then they told us that the actual formula, so this is our answer for A, this is our empirical formula. But it told us that the actual formula, the empirical formula, the molecular formula has 12 carbons. So we know it's C something H12O. And what did they do to get 12? They multiplied by 6. So the actual answer must be C, 1 times 6 is 6, 2 times 6 is 12, 06. And that is our molecular formula.